Okay guys, so alright, so we go back to these Bessel's equations, and this time we're going to do the Bessel equation of order mu. So I'm not going to go that much into all the details. You can look at the previous video or at the previous notes, but let's go ahead and start with this one. So given the second order ODE of this general form, so this is a general form for the Bessel equation of order mu, okay? Oops, I forgot the y over here. So we did of order 0, that means that this term was equal to 0, so we only had x squared y. Alright, so we can rewrite as second derivative of y, we divide by x squared plus 1 over x dy dx plus x squared minus mu squared over x squared times y equal to 0. Okay, so basically we know that this function is singular at x equal x sub naught, and this case will be 0, but it could be any point. All right, so note that in that equation we have px equal to 1 over x and qx equal to x squared minus mu squared divided by x squared. All right, so let's check if we can apply the Frobenius method. So in order to do that, what we need to do is the limit of x minus x sub naught by definition, p of x when x go to x sub naught. So this limit is to be finite. So that means that limit of x when this goes to 0 of x of 1 over x. So that limit will be 1. And the other one is that the limit as x go to x sub 0 of x minus x sub naught square q of x will be equal to the limit as x goes to 0 to x squared times x squared minus mu squared over x squared, which would be what? So in this case, you see you have the x, previous one cancel, here this one would cancel with this one. So the x squared will go to 0, so everything will go to minus mu squared. So both limits are finite. And the other thing we know, if you look at the notes for the Bessel equation, we can say this term is p minus 1 and this one would be q minus 2. All right, so that means that if the two limits are finite, we can assume Frobenius solution, which is y of x would be equal to the summation n equal to 0 to infinity of a sub n x of n plus k. Okay, so if you calculate the, let's say, let's do it one more time, the dy dx equal to the summation of n equal to 0 to infinity a sub n plus k x of n plus k minus 1, and the second derivative will be summation n equal to 0 to infinity a n plus k n plus k minus 1 x of n plus k minus 2. So if we substitute into the ODE, which basically is that equation over here, okay? This is really the Bessel equation of order mu. So if we substitute into that equation, we're going to get the initial equation. So we can say that the initial equation is obtained. Okay? And that initial equation is of the form k to k minus 1 plus k to the p minus 1 plus q minus 2. Okay? If you remember how to do that, go to the previous videos, the one Bessel equation, and I do the derivation of that equation. So we substitute the p minus 1, that is equal to 1, and this is equal to minus mu squared. What do we get? We get k squared minus k plus k minus mu squared equal to 0. So the k's will cancel out, and basically we get that k squared equal to mu squared which means that k will be equal to plus minus mu. Okay, or if you want, k1 will be equal to positive mu, k2 will be equal to negative mu. Alright, so that means that we'll have different type of solutions. So solutions are, we're first going to look at the case of so let's say case A. Let's say that mu is not an integer, okay, or not element of n star, which is n equal to 0. So in that case, we know that the solution will be of the form y1 of x will be equal to the summation n equal to 0 to infinity a sub n x of n plus k1, which will be summation 0 to infinity a sub n x of n plus mu. And this will be equal to C1, Bessel function of the first kind of order mu j to the x, and y of 2 x will be equal to the summation of n equal to 0 infinity a sub n x of n plus k2, that will be equal to the summation of n equal to 0 to infinity a sub n x to n minus mu, which will be equal to C2 j to the minus mu times x. Okay, where, as we just mentioned, j sub mu of x and j of sub mu of x are the Bessel's functions of the first kind of order mu and minus mu. Okay. So that function over here j mu of x, if you do the, basically, if you go in detail, substituting this into the ODE over here, all right, and doing all the calculations, you will find that the power series expansion of this one is summation n equal to 0 to infinity 2 minus 1 power n x over 2 to the 2n plus mu divided by the gamma function of n plus mu plus 1 times n factorial. Okay, this is when mu is not an integer. Okay, and gamma is the gamma function defined as what? So gamma of y plus 1 is equal to the integral from 0 to infinity of x of y e of minus x dx. Okay, so this gamma function has some properties. But again, you don't really need to know all this stuff because the program, so some tables will give you right away the value of these functions here. Okay, as I will show you in a second. Or at the end for the what would be the plot of these figures. So some properties are that gamma of y plus 1 is equal to y factorial, which is also equal to y gamma of y, and gamma of 1/2 is equal to the square root of pi. Okay, so now we're going to look at the case where mu is an integer. So that would be page 194. All right. So case B will be mu is an integer so in that case, we know the solution y1 of x is summation n equal to 0 to infinity a sub n x n plus k1, which will be equal summation of n equal to 0 to infinity. So the same as before, a sub n of x n plus mu. And again, we know this will be equal to j mu. So the first order Bessel function of order n. Okay, so first kind Bessel function of order mu of x, and now y of 2 of x will give you that this is equal to the n equal to 0 to infinity, but we change the coefficient here, b sub n of x n plus k so k1, k2 plus a constant d y1 of x log of x, and this is equal to C2 Bessel function of the second kind of order mu of x, where this function here is the Bessel function of the second kind of order mu. Okay, let me go here for a second. Okay, so let me go back here for a second. This is mu, this is correct, but let's just say this will be mu over here. So this is kind of similar to the solution where you have repeated the roots, okay? But this time you need to add a constant over here. But again, it's not a big deal because we'll always be dealing with the function y, which is the Bessel function of the second kind of order mu, and you will find that from tables. Okay, so let's see. So when mu is an integer, the first Bessel function of the first kind of order mu is given by summation and equal to 0 to infinity. So if you had to do the power series expansion, this is what you will find over here. N plus mu factorial times n factorials. So this is when mu is an integer. And now the relation for the Bessel function of the second kind of order mu. This is a long equation. So the power series expansion will be is given by 2 pi j of mu of log x plus gamma, where gamma is the Euler constant, minus 1 over pi summation to k equal to 0 to mu minus 1 and minus k minus 1 factorial over k factorial to x over 2 2k minus mu minus 1 over pi summation of k 0 to infinity to the minus 1 power n h of k plus h of k plus mu divided by k factorial then k plus mu factorial of x over 2 2k plus mu. So this is really the form of the Bessel function of the second kind of order mu is given by this. Okay, what this value here is the Euler constant, which I think is 0.547 something. Okay. All right. So now I'm going to give you again some properties of the Bessel function of the first kind. So the gamma plus 1 equal to 2 to the gamma over x. I mean, the reason I do this property is because you can do a lot of algebra with this, even though we're not going to do it in this class. And the x of Java mu of x, so the derivative of this is 1/2 of j of u minus 1 of x minus j of v plus 1 of x, which basically this means, okay, that the derivative of the 0x equal to minus j1 of x. And maybe let me stop here 1 second, because I want you to realize something, okay? I know these functions look extremely complicated and so on, but I think I mentioned it on another video. Let me see if I can come over here. Close this one. So this is the modified Bessel. That's not the one I want to look at. Is this one here. Okay? So if we open this file, we run it. Okay, so is it an error here somewhere? No, okay, just took some time. So this is of the second kind, but we're not interested for that now. What I wanted to show you is that this Bessel function of the first kind, they kind are harmonic functions, so they change. They're like a sine and cosine, okay? So the same thing, you know that the derivative of the sine is the cosine and the derivative of the sine is minus the cosine. There is relation about these equations at the same thing. So if you look at it, this is basically what I'm saying. The derivative of this one is minus the other one of the function. All right. So when we look at the figure, that will mean, I guess it's this one here. Okay. So this one has as derivative the one of this one here, the negative of this one. But most important here is that you see that all these functions here, okay, they are sinusoidal. So if you think the response of your system is going to be of this type, so the solution will be under the form of what? Of the Bessel function of the first kind, okay? If you have a solution where, if you want, is diverging to a certain value, oh, here's the same thing, that at 0, when it's 0 is singularity, so there's no value at the at 0, but then you find a stable answer over here, it will be, the answer should be in function of the Bessel function of the second kind. Okay? So let me close this. And now let's go back at the one I really wanted to open, which is, oh, this is the modify. So I think we're good. So basically in this figure here, I'm going to rerun it. I want you to realize that the Bessel function of the first kind will be of this shape over here, and the one of the second kind would be of this shape over here. Okay? All right. So let's go back over here. So I think I'll show you a little bit in advance what is the next topic here, which will be the modified Bessel functions. So when I look at the modified Bessel functions of order mu. Or we could say modified Bessel equation of order mu. Okay? So Bessel's equation and its solution for complex arguments of x is obtained through a change of variable. So basically you are given the form of the Bessel function, which is this one over here. Just going to write now, this is the only new term here, which is m square x square plus mu square y equal dx. So what is the only difference with the one before? It's that we have a minus sign here instead of a plus sign. Okay, so how can we make this to be a positive sign? So in order to do that, you can just say let z equal ix, which will give you that z square is equal to what? Minus x squared. And here we're just going to look at this term over here, okay? So that the above equation becomes x squared d squared y dx squared plus x dy dx plus, because this becomes minus, okay, so this term will become positive over here, will be m squared, oh, I did a mistake here, z squared minus mu squared equal to y, but here we're going to modify this one by z, and this one will also be z. Okay, so we don't have two variables. So this is the equation for the modified Bessel function. Okay, so solution to modified Bessel equation is, okay, so we're going to have again the cases of integer and not integer, but I'm going to do a little bit faster. So y of x will be equal to c1 Bessel function of the first kind and z plus c2 Bessel function of the first kind of order minus mu of mz. So this will be for mu is not an integer like before, no changes, okay, and then for this one will be c1 j of mu of mz plus c2, this is the same thing as the Bessel function of the second kind of mu of mz if mu is an integer. So really here I should put a z again. So again, what do we know? We know z equal to x. So really if we write this on the x, it will be y of x or ix, and we can leave it here. Y of x will be equal to, oops, should have done. So this one will be equal to c1 j of mu I mx. So you see this is supposed to be a complex number, plus c2 j of minus mu I mx if mu is not an integer, and this is equal to c1 j of mu I mx. So I'm not changing anything, plus c2 Bessel function of the second kind of order mu I mx if mu is an integer. Okay, so these functions here are complex. All right, so what's gonna happen is that we're gonna have y, let's see, y of x will be equal over here to what? Will be equal to c1, but instead of using j of mu of I mx, we're gonna have I of mu of mx plus c2 I of minus mu of mx, and this one will be c1 I of mu of mx plus c2 k of mu of mx. And again, this would be if mu is not an integer, if mu is an integer. So over here right away, what you see is that this complex function here, j of mu of I mx, is equal to I of mu of mx, and j of minus mu is equal to minus mu, and the second, this one is this one. So what would be the name of this one? Will be IV, will be what? Modified Bessel function of the first kind of order mu, and the k will be what? Bessel function, modified Bessel function of the second kind of order mu. Okay? And then I will show you on a plot how does these two functions looks like. Okay, so where I of mu of mx is the modified Bessel function of the first kind of order mu, and k mu of mx is the modified Bessel function of the second kind of order mu. Okay. So now, what would be the power expansion of these two functions? So where the power expansion of these two functions will be what? So j of mu of mx, or this will be signed. So j will be I of mu of mx will be summation of k equal to 0 to infinity of mx over 2 factor of mu plus 2k divided by k factorial gamma function of mu plus k plus 1. The I of the minus mu of mx would be equal to the summation k equal to 0 to infinity of mx over 2, but this time will be 2k minus mu divided by the k factorial of gamma to the k plus 1 minus mu. Okay, I'm going to stop here 1 second, see if I can remove this. I'll completely eliminate this. All right. So here we go. We have this one. So now this is important, is that unlikely sorry for that. Unlikely the Bessel functions j mu of x and so the two functions I was showing you over here, see if I can close this. Basically the first two, we had this one here, we had j and we had y, okay? And y of mu of x that oscillates. Alright, I think we'll just show you this stuff. Let's see if I can see it again. It's this one here. You see this one oscillate, the second kind oscillate, and the first kind also oscillate, okay? Now, if I show you the one of the second of the modified Bessel function, so again, this is the second kind, this is the first kind, so you see they behave completely different. This one grows exponentially, and this one also decrease from a logarithmic point of view, or also decrease exponentially. All right. So unlikely the Bessel function j of mu of x and y of mu of x that oscillate, the modified Bessel functions I mu of mx and k mu of mx are exponentially growing and decaying functions. Okay, so again, I will put those figures on the notes, but basically what does that mean? Is that if we go back to this figure here, is that if you have problems that are going to oscillate, where the response will be oscillatory, what would that mean? Is that then in order to find the solution, you will use the Bessel function. So here, this is the modify, sorry, you will use the Bessel function of j. You will use the oscillatory one, the one of j, first kind or the second kind, okay? Depending on the problem. Now, if you have a problem where the answer should be decaying, then you will use what? The modified Bessel functions. If the solution is of this form, if the solution behaves into one of these forms, so probably the solution will be where? Will be probably be given by either the modified Bessel function of the first kind, or will be given by the modified Bessel function of the second kind. All right. So when is this applicable? So we're going to do an example if you want, but this is applicable a lot in heat transfer. And in order to show you, I took over here a heat transfer textbook where basically, let's see if I can go to the camera again. All right, so here we go. So basically this is the problem for, let's see that figure. This will be the type of problem we'll be solving. So it would be a plane wall, a cylinder, and some type of sphere. So if you remember, we say that the Legendre equation generally will be used for spherical problems. So generally Legendre equations will yield to this type of a power series exponential. Cylinders, any type of cylinder generally will end up having the solution of the type of Bessel functions, and this would just generally be given by sine, cosine, or just exponential functions. So here they do a little bit of derivation. All right. So this is the type of equation, the exact equation, but if you look here at the exact equation, here at the bottom, and if you can clearly see, over here for the plane wall, you see it's just a cosine, sine, cosine, or you can rewrite this in function of exponential. But for the cylinder, now it's in function of what? Of the Bessel function, of order 1, but of the first kind. All right? And you have this term here and this term over here. And for the sphere, actually, if you do the expansion of this should be some type of a Legendre function. So how can I remove this? Okay. So we have this over here. And so that will be it. On the next video, I will do a clear example. Oh, just one more thing maybe to finish with this. So let's do a little summary. So over here, let me do a little summary over here. So the first thing we look at is at the Legendre's equation. Okay, and for the Legendre equation, what we had is that we assume the solution to be y of x was equal to the summation of n equal to 0 to infinity a sub n x to the n. But the Legendre equation had singularities at x equal plus or minus 1. Okay, if you want, you can go back to the solutions. You have those Legendre equations, but basically it will be just between minus 1 and 1. So then we say, okay, what happens if you have a singularity at another point? So if you have a singularity at another point, then we look at the Frobenius method, which basically means that the singularity will happen at a point x sub naught. So in our case was always at x sub naught equal to 0. And in that case, we take as a solution y of x equal to the summation of n equal to 0 to infinity of a sub n x of n plus k. Alright, so that is the biggest difference, that the Legendre equation basically is singularities at plus 1 minus 1, and this one is for spherical problems, and this one generally is for cylindrical problems. And we'll do one example on the next video. Alright, thank you so much for your attention.